This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so our next speaker is Thiago Maciel from Technology Innovation Institute in Abu Dhabi, and we are going to hear about challenging of initialization of classical data on a quantum computer, specifically in relation to the Hemingway.
How can I do that? Okay, good. Here? Okay. Can you all hear me well? Where's the thing? Okay, good. Hi everyone. So first of all, I would like to thank the organizers for this nice conference. So today I'm going to talk about our quantum encoder for fixed Hemingway subspaces. This is a joint work with these nice people over here. So you might remember Renato from Wednesday's talk. We also have Jan, Rugi, Sergi, and also our boss, Leandro Aulita. So the baseline of all quantum encoders or data uploaders or state preparation schemes is the fact that we don't want to lose or flush away our potential quantum advantage of our quantum algorithms just by the fact that we overlook this initial state preparation cost. Okay, that's usually overlooked, but this is something that we don't want to do. So the idea here is how can we not spend a lot of quantum resources when trying to upload a data vector X onto amplitudes of a basis B in an exact manner. Okay, the exact part here is quite important because, of course, we can always throw a bunch of single qubit rotations and try to get the encoder right variationally. But then we would need to talk about circuit expressivity or also Baron plateaus. That's not the case here. Okay, here we're talking about exact encoders. So we have some of them in the field. One of them is the unary encoder. The problem with the unary encoder is that it offers no space compression. So we usually don't want to go this route because quantum memory is just too expensive. In the other extreme case here, you might have the binary encoder that you would take advantage of the exponential compression, space compression that it offers. But the problem is that whenever you try to devise a circuit to upload in a binary encoder, you will end up with exponentially long circuits, and we also don't want to do that. So this motivated us to work with fixed Hemingway subspace that lies in a very interesting regime of polynomial space compression. And then I hope, by the end of the talk, to convince you that we might have a way, a not so difficult way, to devise the circuit to do the exact encoding. Okay? So for simplicity's sake, let's assume we want to encode a data vector that is real. Okay? We can also encode complex amplitudes, but would not add much to the talk. So let's assume we want to encode a real data vector that is normalized. In this case, we can always represent a real data vector of a normalized data vector in a point in a sphere using hyperspherical coordinates. So we can always retrieve our data using products of sines and cosines, which is very nice. The other important operational thing about this is that the inverse transformation is also simple. So with a bunch of arctangents, we can move from angle representation and Cartesian representation very easily. So this is one plus of this operational scheme. So the only thing that matters now is how can we construct these amplitudes in this very precise manner. You see, like we need this cascading of sines and cosines in this precise manner to obtain a hyperspherical representation of our data. One way of doing that using RBS gates. RBS gates is something that we know how to compile using two C0s and one controlled RY. This gate creates superpositions of two states, changing only 2 bits, okay? Only 2 bits at a time. And for this gate, for us to define this gate, we need 3 parameters. The first parameter is the theta that we already talked about from hyperspherical coordinates. The other 2 parameters that we need an input register and an output register. The input register will be the bit address that started with 1 and ended up with 0. And the output register will be the qubit that started with the value 0 and ended up in 1 in the superposition. Okay? And we can represent this in our circuit using a compilation-free scheme, like only putting like blue dots for the input qubit, green dot for the output qubit, just putting a theta over here. And that's it. So we now have a gate that changed 2 bits at a time. Now, this leads to the question, can we generate all bit strings for fixed length and fixed Hamming weight, changing only 2 bits at a time? Answer is yes, you can use gray codes. Gray codes are efficient classical algorithms that generate all these bit strings for us, and there are plenty of them, so pick your favorite. My favorite is the one that I know how to implement in the computer. In this case, it's Erdős algorithm. Here, I'm plotting the whole table for 6 bits and Hamming weight 2. And I'm following this to try to construct a circuit for us here that's going to generate all the encoder for this particular case, okay? So we already know the angles, we already know the gates, but we don't know yet where to place these gates in the circuit. But that's exactly what we're going to do now. So take 2 consecutive bit strings from this table. For instance, let's take the first 2 here. Take the first one we call B, the second one called B prime, and let's compare them a little bit. So, reading from right to left, we see that the first bit here started with 0 and ended up with 1. Oh, I already talked about this. This is the output space for our gate. This one started with 1 and ended up with 0. This will be the input for our RBS gate. And then we need an extra requirement here that whenever we have a bit that started with 1 and ended up with 1, we put a control there. So to generate a superposition between 2 computationally based states associated with these 2 bit strings, B and B prime, we need to add an RBS gate, a controlled RBS gate that has the input in 5, output in 1, controlled by qubit 6, and theta coming from the hyperspherical coordinate. Okay? And then you go back to the table and do this for all the consecutive bit strings in the table. Have this horrible thing here, but here is the whole recipe for our encoder. So just to summarize a bit, what are the algorithms to generate an encoder for every Hamming weight key subspace? You first get your favorite gray code, run the gray code, take the bit strings, compare the bit strings in a way that I showed you, so by the end of the day, you will have some bits that will be controls, some bits that will be the input for our RBS gate, and some bits that will be the output for the RBS gates, okay? The other parameter that you need is the theta that comes from hyperspherical coordinates, and then we add the controlled RBS using the controls, input, out, and theta to the circuit. And do this for the whole table that your gray code outputs, okay? So this will be the final circuit for the table that I showed before. Here you can see all these blue, green dots representing the RBSs. Now we also have these violet circles here representing the controls. And you can also note that in the beginning of the circuit, we could remove some of the controls. This will depend on the gray code that you choose. That this only makes sense for some cases. You can check the details in our paper. And that's it. This is the simplest way that I could come up to explain you how our Hamming weight encoder works. So now that we have a circuit, let's encode something. Let's see if the encoder is sound. So we encoded this we deployed this on IonQ's hardware. We tried to encode a Q Gaussian distribution in a symmetric interval between 2 and -2. You discretized it using 15 points. That is exactly the size of 6 choose 2 subspace. And after compilation on IonQ native gates, we used 48 MS gates and 38 single qubit gates to run this circuit. And the result is the following. In the orange curve here, you see area 1 on its best day, okay, without error mitigation. And the violet curve here is the result with our error mitigation scheme that we chose Clifford data regression to do so. And in the lower plot here, we have the relative error to the target point. Okay? So this was just a simple example. We have a follow-up paper right in the corner. But if you have any idea on how this might be useful for you, please come talk to us. We'll be the more the merrier. So we'll be willing to collaborate. It will be very nice. And with that, I can start the conclusion. So we can provide an explicit way to construct a fixed Hamming weight encoder gate by gate, like only providing these gray codes and bit addresses, hyperspherical coordinates, so nice. And then one advantage of this that I didn't touch, that I'm going to touch now, that is the fact that we use the minimum number of parameters to do so, in the way that we are still fully expressive. So for the VQB people around here, would be nice because we have less angles to deal with. We also didn't use any ancillary system here, which is good for the ones that are going to deploy on quantum hardware. And the other thing here is that we know how to compile all these gates here. So it's easy for us to compute all the quantum resources we need for our encoders, okay? And with an encoder like this at hand, we could provide some more fancy stuff, like encoding on sparse and sparse access model, and also on binary. Of course, if you have a Hamming weight encoder, you can stack like Hamming weight 1 up to n, and then you will, by the end of the day, you will have a binary encoder, but I will not have the time today to do so. So yeah, that's basically it. If anything I said here made any sense to you, and if you want to join us at TAI, please let us know. We have open positions. Thank you very much.
Thiago. Questions, please.
Hi, thank you, great talk. I'm just interested, in the follow-up paper, do you try to encode different types of states that aren't Gaussians? Because
in the follow-up, we use the fact that we have a hyperspherical coordinate, derive a bunch of baryon plateau stuff, and right now we are doing quantum chemistry. But yeah, so.
Sorry, really quick. So did you find that there was a difference in the number of gates that you needed from Gaussian states to like other types of states that you were encoding?
Can you say that again?
In the scaling of how many gates you need after compilation?
It's linear in the number of parameters, usually. The scale.
Okay,
yeah.
Cool. Thank you.
I will invite Jonas to come get up, and this question will be very quick, please. Thank you.
Hi. I wanted to ask, what are the advantages that you can get with this kind of model as compared to just arbitrary preparation of states of this kind in terms of computational complexity? And where are the bottlenecks?
The advantage is the fact that we have an exact encoder. Okay, so usually for Hamming weight, fixed Hamming weight subspace, I think we have only 2 exact encoders. This one and the one that is the title of the paper is like Bethe-Ansatz. So we don't have too many encoders that have an exact encoder. So this would be one thing. And the other thing is the fact that we can count. So if you look at our paper, using these gates, they are simple gates, we can have good estimates that would be linear in the data size. So we don't claim to have like super advantage, but we claim that we have something that is easy to count. Okay.
Thank you. Let's thank Thiago again.